Hey everyone, we're going to continue our discussion in this unit and we're going to start talking about gravitational force. Now, we kind of already talked about the gravitational force for a bit. We did a simplified version of it though. So, going back, we talked about how Newton came up with his idea of forces through the idea of the apple falling on his head and also just considering the moon and whether or not it's falling towards Earth. And this is kind of how he came up with the concept of gravity. And he realized that all objects of mass exerted an attractive force which he called the gravitational force. Now, it turns out, we said this in the previous unit, that there are four fundamental forces, that every single force can be kind of categorized as being one of these four. Uh, that the four being the gravitational force, the electromagnetism force, the strong nuclear force, and the weak nuclear force. The gravitational force happens to be the weakest of the four fundamental forces. Now, quick side note, it turns out that with the modern physics interpretation, the gravitational force actually doesn't exist as a real force, but we're not going to get into it right now. We're going to consider it a force as far as we're concerned. Um, now, the reason why we say that this is the weakest of the four fundamental forces is because it's only really apparent when we start getting to very large objects. For the most part, we can actually notice the electromagnetic force with only just a few particles. We do not need that much charge in order to experience the electrostatic force. But with the gravitational force, we need to be on the order of moons and very large asteroids and planets before we start to notice any sort of effect. Um, now, the strength of the gravitational forces ends up being proportional to the masses of both the objects. So both masses will play a part towards this gravitational attraction. And the other thing is that the strength is going to be inversely proportional to the distance squared. That's what they refer to. So this is going to be our equation for the gravitational force between two objects. I tend to call this the big G equation. Now, this is considered the general form of the gravitation force. The one that we've been using, Fg equals mg, is what's considered an approximation. See, we don't need to use g m1 m2 over r squared when we're talking about things roughly on the surface of the planet, because there's really not going to be much differences between how far apart we are from us to the center of our planet. Even if we kind of go to the tallest mountain or building, the distance is not that big compared to the size of the entire Earth. So for those purposes, when we're on the surface of a planet, it's easy to just figure out what g is, and then we can use the simplified version of mg because, well, the g isn't changing because all these other factors like the mass of the planet, the distance that we are from the planet, and this big G term all stay constant, while the little mass is the one that's changing, like our mass is changing. But this is the general form of the equation. All right. This big G term, what is that? That is the universal gravitational constant, and it is 6.67 times 10 to the negative 11 meters cubed per kilogram second squared. This is a constant term. It is given on the front of your reference table, so you don't need to memorize it. Uh, do not confuse this G with little g. Make sure that you don't accidentally put 9.8 for this or 10, because you will get the question wrong. And like I said, the only time you're really using this equation is when you're dealing with, I was going to say, only with the really large planets, force between the Earth and a satellite, Earth and the moon, a planet and its moon, or multiple stars, two different stars. But I did also think that they could throw this equation in when they start talking about particles, oddly enough. But that's usually done to kind of show the sheer difference between the gravitational force strength and the electrostatic force. So typically, when you start talking about the gravitational force and it's between two objects separated by a distance, that's usually a very clear indicator that yes, you're going to be using this big G equation. For every other cases, like the normal cases when you're on the surface of the planet, you can feel free to use Fg equals mg. All right. And R, one thing I want to point out, R does not stand for radius. It stands for the distance between the centers of the masses. This is extremely important to keep in mind, that it doesn't refer to the surface edges. It doesn't refer to the radius of the object. It is distance between centers. All right. I know a lot of you see the term r and you think radius, but do not think that. This diagram actually shows what we mean by the distance between centers. It's not taking from here to here, but from the center of Earth to the center of the moon. One thing to keep in mind is that for the most part, the equation works by essentially assuming that all the mass is concentrated over at that center of the planet, at the very middle of it. For the most part, it ends up working out that way, so don't overthink it. Um, the other thing to keep in mind is that the equation has an m1 and an m2 that refer to the two different masses. But you'll notice I didn't really mention what m1 and m2 are because it doesn't matter. It doesn't matter what m1 and m2 are because, as we know, when you multiply two numbers, it doesn't. The order doesn't matter. So it doesn't matter if you say that m1 is the mass of the Earth and m2 is the mass of the Moon, or vice versa, because you're going to get the same number anyway. So it turns out that the force is going to be the same, which actually makes sense because this is exactly what we expect from Newton's third law, that the gravitational force that the Earth exerts on the moon is the same as the gravitational force that the moon exerts onto the Earth. So these forces will be equal and opposite. The other thing is we can kind of combine this with the other FG equation, Fg equals mg, to come up with an equation for the gravitational acceleration on the planet. Now, this isn't on the reference table because, again, it's something that you can kind of easily derive by just taking the two Fg equations and setting equal to each other. But what you end up doing is just taking the two equations where when you use the FG, it's m of the object that you're referring to, and g being of the planet. And then when we kind of put subscripts onto the other terms, one of the masses is for the planet, one mass is for the object. You'll notice we have two masses of objects on both sides, so they cross out. And if we want to find a equation for the acceleration and gravity on a planet, it will look something like this. So this is how we can determine what the acceleration would be on the surface of the planet without ever actually stepping foot on there. All we need to know is their mass and the in this case the radius of the planet, so that we know where the surface of the planet is. Now, one thing I did want to point out is that I kind of hinted at this previously, but this equation is notorious for using what's called the 1-1 method. This and the circular motion, I didn't refer to it then, but I'm going to refer to it now. Basically, the idea is they like to ask questions like, hey, what's going to happen to the force if I change the mass, or if I change the distance I am away from the object? Like, I double the distance. What happens to that force? So there's a few different ways that you go about solving these problems or answering these questions. However, the easiest way that I recommend doing it is called the 1-1 method. Now, the way you do it is that you plug in a 1 for every single variable that stays the same, and then you plug in a number to represent what happened to that term. So if something was doubled, you put in a 2 in. If it was quartered, you put in 1/4, the fraction 1/4, and then you basically solve it. And then whatever your final answer is, it tells you how much bigger or smaller that new number is compared to the original. One thing to keep in mind is that every single term, even if it's a coefficient like a 1/2 that was thrown in there, is also, you kind of put a 1 in for it. Another way to think about it is you erase every variable, every single term that isn't changing. You only look at the variables that are changing, and then you plug in either, what factor they change by. They change by a factor of 2, then you put it into 2. All right. So here's the first question. Pause video, work itself, and we'll go over a second. All right. So here's a perfect example where we can practice using the 1-1 method. Here they tell us that the distance between two particles is doubled, and that we want to know what happens to the gravitational force between them. So we look at our equation, Fg equals g m1 m2 over r squared. All the terms in the very top stay the same, so the g, m1, and m2 all become 1s. If I want, I could have also just erased them and ignore them. And the only term that actually changes is this distance. And they said that the distance is doubled, so I'm going to put a 2 in for that to represent that it was doubled. It was increased by a factor of 2. Because that term is squared, I have to square the 2, and that gets me 1/4. Now, 1/4 isn't my answer. My answer is 1/4 times the original force. So another way I could say is that the force of gravity was quartered, or it decreased by a factor of 4. These are a variety of different ways I could say the same thing. The main point is that I know that by doubling the force, not only have I decreased, by doubling the distance, I've not only have I decreased the force, but I've decreased it by a factor of 4. All right, here's the next question. Pause the video, work itself, and we'll go in a second. All right, so you might think that this one ends up, it's going to be a little bit tricky, or we can use the exact same method for the mass. However, we don't need to do that because one thing we know about the mass is that as we go from the surface of the Earth to twice the radius of the Earth, the mass stays the same, right? Now, to determine the weight, now this one actually gets really tricky, and we have to pay attention to the wording of the problem. So, for the most part, this is a very similar setup to the prior question, where the only thing that's changing is the distance. So, my question is, by what factor is my distance increasing by? Now, you might think that it should be increased by a factor of 2 because it says twice the radius of the Earth. However, notice that it says that it's transported to an altitude that is twice the radius of the Earth. That altitude means that from the surface, it is now twice as far from the surface. But remember, r represents the distance between the centers. So I actually have to think about how many Earth radiuses is it to the center. And if it's twice above the surface, plus the one radius to the center going to the surface, that means I've actually increased my distance by a factor of 3. Here's a good representation of that. So the altitude is twice the radius, but if I include the radius towards the center, then I end up getting a distance of 3r. So I put a 3 in for r, and I end up getting that the weight actually ends up being 1/9 of the original value. This time they told me that the weight was w, so I'm going to say it's 1/9 of w. All right, here's the next one. Pause the video, work itself, and we'll go in a second. All right, so here's a good example of how we can kind of use these equations to kind of roughly estimate what the acceleration is on another planet. We have an idea of what Pluto's mass is and its radius is compared to Earth. So if I want to find the value of g, what I do is I use the slightly altered version of the gravitational force equation. I plug in the mass as being 1/500th of Earth's mass, and the radius being 1/5 of Earth's radius. Plug all this in, and I get that it ends up being 0.05 times the value of Earth. So I end up getting that the gravitational acceleration on Pluto would be 0.5 meters per second squared. I'm just going to leave it at that. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.